we're going to be able to confirm this. Okay, we're going to take a nice RxX. Okay, compute the eigenvectors of that RxX, and you'll be able to observe that it's very close to the basis function of the DCT. Okay, so then that's why that explains why the DCT is very dominant in image and video coding. Okay, so the summary, optimal transform comes from eigenvectors, eigenvalues decomposition. Okay, and the KLT is nothing more than a set of eigenvectors of the input autocorrelation matrix. The correlation matrix RxX. Okay. Now, to construct a good basis means you have to come up with a good signal models and try to use the same set of basis function on both sides. Okay. So one of those good models is the AR1 model that we used before, and it turns out for that AR1 model that we use, the DCT is a close approximation of the original of the KLT. And the DCT has many different types. Okay, so this is quite similar to Fourier transform, right? But you notice that there's no EJ omega anymore. Okay, so we only have the cosine part. We don't have the sine part, and it's real. It's not complex. Okay, and it's not just the real part of the Fourier transform. It's not the real part of the Fourier transform. It's a little bit more than that. Okay, so this is the type 2 DCT. It's the type of transform being used in JPEG and MPEG. Okay, and this is the definition. Okay, so the type 2 DCT matrix is this. The index of the matrix is M and N, and if you substitute M and N in, M goes from 0 to M minus 1. So this is of size M. This matrix has size large M. Okay, you have different cosine being sampled at different locations. Okay. Furthermore, you have cosine of different frequency. Okay, so you can think of M here as taking care of the frequency. So having larger M means you have cosines that oscillate more. Okay, so this typically the basis function of this guy. Oh, I'm going to have it in the next class. Okay, so the basis function look like this. If I plot the basis function, it will look something like this. Okay, by increasing M, you increase in frequency. Okay, and this N represent the index in the sampling in time of these cosines. Okay, so this direction is M, this direction is M. It's an 8 by 8 or M by M, large M by large M transform. JPEG use 8. Pick M as 8. And a block has 64 samples of pixels grouped together, okay, being processed together using this 2D DCT transform. And typically the behavior is like this. Okay, this is called DC, or the average of the block. Okay, Y average. The first basis function is all frequency 0. Okay, all the samples get weighted the same way. Okay, and if you do it all the columns and then all the rows, it just gives you the average of the block, right? Which is nice. Okay, at least you know the block is dark or bright, or okay, but it doesn't have any information about how the block behaves. Okay, it's just the average of all the pixels in the block, and that's the DC coefficient right here. Now all the low frequency guys will be right here, right? The guys that has more little m will be right here, and then all the high frequency guys will be right here. The middle frequency guys will be right here. Okay. It turns out that all the horizontal edges will be somewhere here, and all the vertical edges will be somewhere here. Okay, why is it vertical here but not horizontal here? You can think of these bases as the way that you compute the coefficients by doing the convolution of the bases, right? So if you have edge at the vertical direction, and you do convolution across, you pick up large energies, right? So that's why they are up here. But if you have a lot of horizontal edges, and you do convolution this way, you pick up a lot of energy here. Okay? So in the transform coefficients, it's reversed, right? A lot of horizontal energy will go here, a lot of vertical energy will go here, and the typically behavior of a block is that most of the time you have large coefficients here, and a lot of zero or small coefficients over here. That's why you can throw them away. You only keep a few guys up there. Usually we always keep DC, right? Right? The average is very important. The average is very important, right? It tells you that the block is black or white or whatever. That's the fundamental information of a block. And we always keep DC, and then we keep a few more low frequency coefficients. Okay. Now, questions. If I have a block that has no variation, okay? For example, all gray, okay? Or all black or all white. I feed it through the DCT, what do I get? Only DC. Only DC. Why?
Because of the frequency.
Right, because when you do convolution of a constant sequence with all these variations, they turn out to give you zero order. Okay, so if the block has no variation, you only pick up one guy, which is the DC right here. Everything else will be all zero. So that's a tremendous amount of compression, right? You will keep one out of what? 64. You keep one out of 64 and you get perfect reconstruction. You keep one out of 64, but you get perfect reconstruction. Now, in natural images, a lot of times we encounter this situation, right? I take a digital camera, I take a snapshot maybe right here. Guess how the wall behaves? Constant, right? Constant. So in that case, we have 64:1 compression at least, at the minimum, okay? And we have perfect reconstruction. Okay? So that's how we do compressions in practice. Now, there are several interesting properties about the DCT, and some of them I asked you to prove, okay, in today's assignment, written assignment. The first interesting properties is the symmetry, okay? And so I have some of the sketchy proof right here, and I want you to expand on it, okay? There's another nice properties regarding the recursive properties of the DCT. And we encountered this problem before with the DFT, right? How do people get the fast Fourier transform? People get FFT based on the factorization into smaller guys, right? Instead of doing an n-point DFT, you do 2n/2. Right? You do 2n/2 DFT, and then you keep on breaking it down. The DCT also have some interesting properties, and you can show that in order to implement an m-points DCT, you can do 2m/2 points, okay? But one is type 2, one is type 4. The type is in the previous two slots, okay? Just different sampling. So that's another property that I want you to show. Okay? So in a very high level diagram, we have something like this. Okay? You take the difference, and then you take a smaller DCT here, another smaller DCT here. So that's another property. Now, this is a typical implementation in practice. People don't do matrix multiplication when we implement the DCT. We don't do matrix multiplication. Just like we don't do matrix multiplication when we have to take the DFT or something. we actually break it down you probably recognize this, right? It looks like DCT, FFT style implementation, right? So you break the bit matrix into smaller ones, okay? So this is a typical fast implementation of the DCT, and these C stand for cosine. So this is cosine of pi over 4, which is square root of 2 over 2. This is sine of pi over 4, which is square root of 2 over 2. This is cosine of 3 pi over 8. This is sine of 3 pi over 8. So on and so forth. So people actually do a lot of investigation and come up with factorizations of the DCT matrix like this. So this is pretty typical, and you can count that in order to implement this, you need about 13 multiplications and 29 additions for 8 input times. Okay? That's it.